in this celebration of the 50th year of this institution. I'm very grateful for the organizers for inviting me here. This is my first time in Madras or Chennai, but I'm particularly happy that two of my teachers, which was a complete surprise, that they would be here, Professor Mani and Professor Ramchandran at IIT Kanpur. And I feel that what I'm going to tell you today, I'm going to remember one more colleague of yours, Professor Deshpande, Abhay Deshpande, who is really the one who told me that there was some field called experimental physics that you should also consider. And I seriously took that, and it turns out that that's what I've become. I've made this talk, prepared this talk based on three things. I think this problem of nucleon spin, some of the people who are senior in the room might know everything about, but it is not something that is very well known in Indian scientific younger community. So I'll give you a brief introduction as to what the problem was and what it is that we are trying to understand. In the second part of the talk, I will give you a brief flavor of what is the current investigation, again experimental investigation, going on, and what are its limitations. And then I will talk about when you grow up, and if you try to be in this field, what are the opportunities that might be available to you for your careers in the next 10 to 15 years. So I'll give you a brief review of this whole thing, starting from the introduction to the current and to the future. I've also tried to give you a flavor of the experimental method that was developed, that had to be developed. Often in physics, you have to develop ideas for measurements when they are confronting you. And this was a very ideal case. That was really something that was very challenging, but also exciting. So I'll try to give you some of these techniques that we develop in the next 10 years, which we now routinely use in the collider called the relativistic heavy ion collider in polarized mode. These were things that didn't exist in 1998 when I started really working on it. They developed in the next 5 to 7 years, and the physics that is now flowing out is based on those. Some of them are accidental, and I will tell you which were accidental and which are real. So this is just a story of spin in that sense. First thing I want to emphasize is that spin and rotation is often counterintuitive. And when you see something that is associated with rotation in nature, it makes you think. And I'm going to show you a clip of something I filmed in my office, and you're going to think about it in the back of your mind and keep that thought through the talk. And today during the excursion, we'll discuss what the mechanism of this is. So this is called a levitating top. How many of you have seen this? And how many of you understand it? Okay, I don't see anything. Okay. All right, so let's see what this is. The idea, that's a plastic top with a metal surrounding on it. There are some magnets here, and it's rotating. It's not hanging, it's rotating. It's not magnetic levitation, but close. And there's a clue coming up to you. Just be careful, now see. There's a clue as to how this works and why I'm showing you in this talk. When the rotation ceased or the speed went down, it dropped. Okay, that's a very big clue to you. All right, so if you're curious about spin, you're not the only one. You are in great company. Let me show you the company that you're in. This is a picture from 1955 where Bohr and Pauli are trying to understand the dynamics of something called a tippy top tie. It's a top which spins at some point in angular momentum, flips over, and actually starts rotating, just a complete flip. So it's a very interesting talk, and this is a picture that is made famous. All right, let's go to the next one. Here are, I thought, effects of experimental things that we saw in the last century that changed the way we think about physics. First was the Gehrlach experiment in 1921, which discovered the space quantization associated with the direction. Gauss-Smith experiment in 1926 that told us something about the atomic fine structure, the electron spin magnetic movement. Stern's experiment in 1933 that told us that the proton's anomalous magnetic moment is unusually large, that told us that the proton was not a point particle per se, it had to have some distribution, a structure. Cush's experiment in 1947 that told us, as against that, for the proton, electron's number was extremely small, that told us that the electron was probably a point particle right there. Then there was the SLAC experiment that was led by Charles Prescott et al. At SLAC. They did an ED scattering, parity violation ED scattering, single spin asymmetry measured when one of the particles is polarized, that gave us the indirect hint of the parity non-conservation that led to finally, eventually, confirmation in direct way of W's in electroweak physics. And the last one was in 1989, which was a European muon collaboration discovering something that we call the spin crisis, and this is something that I will talk about today. Experiments with spin have fundamentally changed the way we think about physics. It can be hence argued that the 20th century was a century of spin surprises. In fact, two stalwarts in this field who have spent a lot of time and effort in understanding the Nucleon spin have commented that experiments with spin have killed more theories than any other single physical property. This is Elliot Leader of Imperial College London. And J.D. Durkheim commented that if theorists had their way, they would ban all experiments with spin, because every time you make a model or a theory, the experiment comes along and it destroys that theory. And I will show you, we will see that position of spin destroying the concept of existing concept continues even now. So, first, an introductory slide on deep inelastic scattering, or what is an electron scattering off of targets. So most of the things that we know about the structure of matter, in the early part of the 20th century at least, we know from lepton beams hitting at different energies on fixed targets. And first was the elastic lepton nuclear scattering that told us that the nuclei and the nucleons have finite sizes, they call the form factors. Then we discovered through inelastic scattering that protons have internal structure. These experiments were done in the late 1960s that led to Nobel Prizes in 1990 for three gentlemen. So this method was known and reliably used in the early part of particle physics to understand the structure of matter. What is that method and why is it so popular? So I'm going to show you some basic things about that method that I will keep using during the talk. This is the Friedman diagram, or a representation of elastic scattering, or the deep inelastic scattering in this case. An electron beam is coming through and gets scattered through an exchange of a virtual photon with a proton. The energy exchanged is in this represented as Q squared. Okay, it's the measure of the resolution power of what is the detail that you want to see of this proton. The scattered electron goes with an angle theta e and the scattered electron energy E prime. And as an experimentalist, you will want to measure the scattered electron energy and angle as precisely as possible. And that's your limitation, how much money you have, what kind of calorimeter you want to build, how much acceptance you want to accept around your interaction region, and that determines everything about that. Now you start reconstructing all the variables that are essential for your knowledge of that event, what happened in that event, and you will see that the Q squared is a function of the initial energy of the electron beam, which you probably know because you created the beam to make the experiment. The E prime is the scattered energy, which I just told you, how well you build the calorimeter will determine it, and the scattering angle is also something that you measure. So this Q-square variable, what happened, what was the interaction between the electron and the proton, was completely determined by this Q-square, by this single method where we built a good calorimeter. This is a very powerful tool. Then we start looking at what was the measure of inelasticity, Y. And you will see that this is also dependent on the scatter energy and the scatter angle divided by the initial energy. So again, just by building and looking at the scattered electron, you have determined this Y variable as well. Then the third variable, x bar k, which is Q squared divided by S times Y. Q squared we just determined, Y we just determined, and S is the square of the center of mass energy of that system. And that you presumably know as well, because you know the initial energy of the electron and the proton, you can determine this as well. So, in one shot, by measuring the scattered electron energy and the scattered angle, you determine everything that you wanted to know about that detector, that collision. And you can do this event by event. So, really, really powerful tool. The inclusive events are they called when you only measure the scattered electron, but you can be more ambitious and say, I want to see what happened to the destroyed proton. What came out? Pions, kaons, in what ratios, what energies, what angles. Then you need other parts of the detector, and those are called semi-inclusive events, semi-inclusive deep inelastic scattering. You become more ambitious. And then you become even more ambitious and say, I want to measure everything about that event and build a detector that is 4 pi with all the bells and whistles, and you can, those kind of events are called exclusive physics measurement. Everything in that event is measured. So this is going to be the initial tool and the final tool in my talk. In the middle, I will divert. So, when we know that the proton is a bound state of something, quarks and gluons, this was the prize given in Nobel Prize in 1990 given for the quark model, and this was the statement, deep inelastic scattering of electrons and protons and bound neutrons has been essential and important to the development of the quark model. In those times, people were able to explain most properties of the hadrons, as you probably heard, in terms of, in the lecture last night, in terms of simple naive quark model structures. We knew the property of the quark, they had to be fermions. There were other things that we know about the quark model at that time, and you could reconstruct almost everything about the hadronic structure and the properties. But what about spin? Well, could we understand the property of the proton like spin in terms of this quark-proton model? And attempts were obviously made. The proton spin is half. Each quark is a spin half particle. So the most naive picture people had was that you have 3 quarks which were imparting the properties to the proton. The only very simple and obvious way, which normally what the physics works, is that you have 2 quarks pointing upwards and 1 pointing downwards, and that just simply adds up with various quantum mechanical additions to the total spin of the quark. And this is called the quark's contribution to the Nucleon spin. The sigma, and I will use this is a historical representation, I will use this in my talk, during the talk. So this was a simple assumption that was made. I have very few equations in this talk in the theoretical side, but this is one of them. I have to use them to introduce some of the concepts. So the lepton-nucleon cross-section is written in this part here. There are 2 parts to it. There is a leptonic part and there is a nucleon spin part. And then this is the lepton tensor L mu nu affects the kinematics. It is purely a QED term. And the hadronic tensor W mu nu has information about the hadron structure. And that hadron structure has parts which are called the structure functions. The F1 and F2 are the unpolarized structure functions that tell you what is the quark's momentum structure inside the proton. How are they, if a proton is moving with a certain momentum, what fraction of them are carrying this fraction x here. But they are basically about not related to spin, but related to just the momentum. And then there are these terms here, which are the spin structure functions G1 and G2. The G1 is the one that I'm going to be talking about mostly here, which tells you if the proton is spinning in a particular direction, how many of these quarks are aligned with it and how many of them are anti-aligned with it. And because every time you won't have all the quarks aligned with it, some of them will be anti-aligned. So I will be trying to measure the spin structure G1 of the proton. The G2 are associated with other factors and they're extremely small. So for most of my discussion and early discussion, I'm going to just ignore that. So F1 and F2 are the unpolarized structure functions of momentum distributions. G1 and G2 are the polarized structure functions and the spin distributions. In the Quark Proton model, you simply have this relation between F2 and F1, and G2 was 0. You don't have to know what that detail of that was. Just to know that this F1 has a representation in which for each flavor, the quark aligned with it and anti-aligned with it was summed over and averaged. And so we write it like this. And in the G1 structure function, this sign here becomes negative. So what is aligned with it and anti-aligned with it, positive and negative, for each flavor comes into picture. So that's the definition of the G1 spin structure function. And I'll be using these again in the later part of the talk. So we define the total quark distribution for a particular flavor to be Q plus minus Q minus, which is for any flavor. Our probabilities of quark and anti-quark with the spin parallel and anti-parallel to a nucleon spin. The total quark spin contribution is then for a proton at least, is mostly being delta U and delta D, and perhaps will be a little bit of strangeness that might exist. And at that time at least, people thought that the entire spin contribution of the quarks would determine the proton spin half. Now we know that there is something else that has come on. My story begins here. How would we discover that something else has to come in? All right, so let's make a simple model and see what happens to the valence quarks and anti-quarks, and how are they responsible, if they're responsible for a total spin. If you wanted to test that hypothesis, how would you do the experiment? Well, the experiment that was done was a simple one. We assume that this is exactly right. As I said, the simple model, proton spin is half. I have 2 quarks or 3 quarks inside, valence quarks, that determine all the properties of the proton in this picture, and I have 2 of them moving up, spinning up, 1 moving down, and you have a very naive, simple model. There are some corrections that come because of the possible motion. We know that there was orbital motion as well already. Those corrections are there, and I will talk about them a little bit, but for this hypothetical, simple experimental explanation as to how we measure it, we don't need to go into that detail. Here. The next one was, okay, the experimental method. Deep inelastic scattering of polarized electrons or muons off of these protons. So you have this proton, and I have developed now a technique in which I can polarize fixed target experiments. So I can get lots of protons in some complicated chemical compound, and I know that there is a predominance. I put them in a very strong magnetic field, I polarize them, I cool them down. There's a full science associated with it, but this is a technique that had been developed in 1960s and 70s, how to polarize protons and effectively use them. Then you have these polarized electrons, and it emits this gamma star, this virtual photon, and then it starts, as long as the wavelength is smaller than the size of the proton, you're starting to see the inside of the proton, and that is what is going on. Now my assumption here, remember, was that there are 2 quarks which are spinning this way, and 1 was spinning that way, and that imparted the spin of the proton. If I have that condition, then the spin 1 of the photon and the spin half of the 2 quarks will have the chance of collisions, and then the quark spin will flip to the other side. If it encounters this round quark, I call it round quark because it is already spinning in my direction, the photon will try to impose more spin in the direction. The quarks are spin half particles. That's not a possibility. So the chance of cross-section here is 2/3 in this model, right? Now what I do is I have controlled the polarization, and I change the spin of the motion of the proton from one direction to the other. If my hypothesis that all the quarks that it had that imparted the spin of the proton is correct, then I should know exactly what to expect. Because now I'm saying that these 2 quarks are spinning in the direction of the photon now, photon spin, and this quark is spinning in the opposite direction. That means now I only have a 1/3 chance of collisions, or actual collisions with the photon. So if I do this experiment, this versus that, I will see a difference in the 2 numbers that I see, how many events I see here, how many events I see here, and divided by the sum. All the spin experiments that I'm going to talk about today are based on this specific thing. I have taken an example of quarks right now. I will talk in the second part of the detector when I talk about the Gluon measurement, exactly the same thing. how many times do I see gluon spinning contributing to a nucleon spin and vice versa. But this is, remember, this is a basic technique. Okay, so now, is that it? Well, it's not simple as that. This is too simple. So let's go one more step. The measure asymmetry I told you was the difference between this combination minus that combination over the spin. Where does it come from? Let's take each of those. Number of particles in the beam, number of particles in the target, times the total cross-section, times the detector acceptance. I didn't tell you the detector was not 4 pi, so I have to account for that. And then there is the detector efficiency. So these are the 4 factors I know. Then the other side, we have exactly the same thing, but the cross-section is now different. And then you can take this ratio, and what you get is this. This is really what you are after. A measure then becomes G1 spin structure of the proton, or connected to the G1 spin structure of the proton. If every term that you can control in this form and that form is identical, because that's the only condition in which all these terms cancel. And this is where the experimental challenge comes in. Why does it matter? Here is, again, a little bit more detail of that. You have a beam which is spinning that way coming from this direction, and you create a target. You create a target with a spin that way, and you start putting a detector on this side, and you start measuring on this side. You did this on December 11th. You went home, and then you came back on December 12th, and you turned the target position the other way, and you did the experiment again. But today the beam was not the same intensity. Accelerators don't behave the same way day to day. And by the way, there was a power failure between 12th and 11th and 12th, and some part of the detector was not functioning as exactly as it was the other one. So the detector acceptance was not either correct. That would not give you the right answer, the right thing that you're looking for. You don't know what the answer is. But you will see something, and you will say, aha, there is a big difference between today and yesterday. But that is not because of the physics asymmetry you're looking for. That's because half of your detector on 12th December is wrong, is dead. So you need to go and make sure that your detector is identical. So the way we do that, the way that it was solved, was that instead of having a single target, they said, okay, let's put a double target. And you spin this part of the target this way and this one that way, and the beam comes in and hits both targets simultaneously on the same day, on the same event, on the same second. Every pulse of the beam sees the 2 targets simultaneously. And then you see events from here and there identically. The distances here from, I'm not showing it to scale here, the distance, the total size of this target here is approximately 50 centimeters. There is the distance between this one and the detector. This length of the detector can be about 50 meters. So this is 1 to 50 here, or 100. But still, there are differences between the angles that are imposed by this part of the target and this angle, whereas this one too. So there are small changes in the acceptances as well. If we're measuring a very small physics asymmetry, which in this case you're measuring, of the order of 0.1 or so, 10%, then you have to worry about the small differences in the angles subtended by this target on the detector versus this target on the detector. The way to solve that was that on December 13th you come in and you flip the spin on this target and that target. Now you have entirely symmetric position again, that this way spinning target now move here. You don't physically move the target there, you just flip the spin. So we keep on doing this. Typically, we used to do this target spin rotation every 6 to 8 hours, and then we would rotate it another time every few days. That was the method used, that was the method developed. And we could measure eventually over years, about 6 years, we could measure small false asymmetries at the level of 10 to the minus 4. We could contain them at the 10 to the minus 4. All right, the experiment was done. This was what was expected. This is the value of expected delta, the value of the G1 spin structure function integrated over the range in X. What we saw was this curve right here in 1989, 1990. And the delta sigma, that the quark-anti-quark helicity combination, came out to be this 0.12 plus minus 0.17 when it was expected to be around 0.6. And this is 0.6 is the relativistic correction that will take it from 1 to 0.7, so lower. But the major challenge was here. First of all, the uncertainty was large, but this was consistent with zero. It was telling us that it could be that the quark spin had nothing to do with the proton spin. When every other property of the proton was determined what you knew at that time was based on the structures of the quarks that you knew. This was why Professor Elliott later called this the spin crisis. And this prompted a lot of experimental investigation in the next decade. However, how significant was this? Well, here are two archaeologists who have just discovered a small hit here. And one is telling the other, it could be the discovery of the century, depending, of course, on how far below this thing goes. So, Professor Leader called it a crisis, but it was crisis in the understanding of the nucleon spin as it existed then. We understood already at that time that the concepts with which we were looking at the proton were insufficient. So we had to develop something else. And to do that, first of all, experimentally, 4 new experimental efforts were launched in the world at SLAC to measure this at very high precision. Electron beam experiments were launched. At Hermes Daisy, this experiment in HERA was proposed. Then there was an experimental facility at Jefferson Lab in Newport News was proposed, and also the EMC experiment CERN developed into its daughter and then its granddaughter SMC and Spin-Muon collaboration and the Compass. Let me take you fast now into the current world. So we have given up on this idea that the proton spin is only given by these 3 quarks, and now we understand that the quark spin is very small. Where is the remaining spin? Well, it has to be that it's bound by the gluons. So Professor Alberelli at CERN said, oh, the gluons must play a significant role. Let's find out what the gluon distribution is. That became the holy grail, the next step. But we also know now that the orbital motion of the quarks and the orbital motion of the glue cannot be ignored as well. How do we find out all of these components is something that is the current picture. So we have evolved our understanding of the nucleon spin from the early knowledge of just delta Q to what we think is the big picture. And these are the 4 components: quark anti-quark distributions, orbital motion of quarks, gluon helicity distribution, and orbital motion possibly of the glue. I told you that we are now looking for a glue. How is the gluon distribution in the proton calculated? Or how do we determine it? Here is a picture of F2 structure function, the unpolarized structure function, which is measured at HERA in a large energy collider, 300 GeV center of mass, electron beams at 30 GeV, hadron proton beam at 800 GeV, 300 GeV center of mass. What is shown here is over a very large range in Q squared. Remember that Q squared, the exchange of photon variable? A very large range from 1 GeV all the way to 10 to the power 5 GeV squared. And a very large X range. X is the Born X, the momentum fraction of the proton that the quark carries. This is 0.65, I'm sure you don't see that number. That means in this range here, the quark is essentially carrying half the proton's momentum, all the way down here to 6 times 10 to the minus 5. So very small fraction of the proton momentum. So as you can see, the F2 structure function is measured over a very large X and Q squared range. And the gluon distribution that is shown here, the proton distributions that are taken out of that data is a result of a global analysis at next to leading order. But the crucial thing I want to emphasize here is that the scaling violation, the slope of the F2 structure function here, gives directly something that is proportional to the gluon distribution function. So the slope of the unpolarized structure function is responsible for the determining of the gluon distribution. So how well can we determine the slope is the question. Now let me tell you what we had, or what we have so far in the polarized Inelastic scattering. On the second plot. Come on, yes. Here is the same plot, F2 structure function, and here is the G1 structure function, the G1 spin structure function. As of 1998, and as of today, it still has the kinematic range which is shown here, about 2 orders of magnitude in Q squared, and about 2 orders of magnitude in x. That entire triangle that I'm trying to show here fits in this corner of the two-structure function plot here. Look at this, the most deterministic slopes, most defined slopes are in the region which we don't have any access to. Which means that if you try to do the same kind of analysis here, to determine a Gluon distribution, you are going to get large uncertainties in your Gluon distribution. And that's exactly what we get. This is a structure of the Gluon distribution. These are the quark distributions which are very well known, very well determined because the quarks sit in the high X region. In the low X is where the Gluon sits, which we don't have too much data. And we're trying to determine the slope of these distributions using the high X Gluon distribution. So this is what it is. And if you evaluate the total contribution based on this plot, which is the uncertainty, the best fit to the world's data with the statistical errors, systematic errors are shown here. These are the experimental systematic, there are some theoretical systematics, but the total picture gives you an uncertainty, the central value of delta G to be 1, delta G is the Gluon's distribution, similar to delta Q or delta sigma, but the uncertainty is now 1.5. Recall that delta sigma we tried to improve and we did succeed. This error bar was 0.17, the central value was 0.12. We've done much better. We've reduced the uncertainty by factors of 4 or more in this part, but now we are going quantitatively after the Gluon distribution. There's a problem with this, right? You're looking for 0.5. You're looking for 0.5. Proton spin is 0.5. I've just told you the delta sigma is 0.23. It appears in that equation as half times 0.23. That means 0.12 comes from the quarks, and the Gluon distribution is 1, which means it's a huge spin contribution to the nucleon spin, which means that the motion, the orbital motion, the only thing that is remaining from quarks and gluons into the system has to be opposite. For some reason, we don't understand. So now the aim is to first reduce the uncertainty on the Gluon distribution function. How do we do that? Well, as I said, in the 10 years, please ignore this. In 10 years of the 1990s, we came to this. This is a large value, but large uncertainties. We need experimental measurement directly to go and reduce the uncertainty. As was said in the previous talk and yesterday, you know that the photon that I just, that is probed on the inside of the proton is colorless. And the gluon is chargeless. So we don't see eye to eye. So if you want to study gluons, that's not a good probe. Or at least it seems not to be a good probe. Unless you go to HERA-like facility where you have a large range in Q square, you can see the evolution of the Q squares. Then you have a chance, but not directly. What would we do then if you want to study the gluons directly? Well, you know that the protons are predominantly gluons. Why not collide protons and protons? Take the same assumption I took before, that the remaining spin of the proton is now carried by glue. So if I can control the spin of the proton this way or that way, I am able to change the direction of the glue inside the proton. And I'll do this correlation experiment, basically this way versus that way. And if I've done the same method that I just told you for the protons, but now assuming that this is the gluon's contribution, and to get to the gluon's contribution, I need high energy protons colliding with each other. And this is where the seeds of the RHIC spin program were sown. The RHIC spin program was promoted with 3 main aims: a direct determination of polarized Gluon distribution via multiple probes. The way we do that, we'll see how many pions, pi pluses, charm, anti-charm, bottom, anti-bottom is created when we collide protons moving that way versus that way. Most of these Platonic collisions are gluon-gluon collisions that give rise to pi QQ bars, and then they fragment into pi zeros or any other thing. So that was the main effort. This is measured using a double longitudinal asymmetry. That means the 2LL means it is longitudinally polarized proton and longitudinally polarized proton. As is shown here, these are the 2 colliding protons. This is the proton spinning that way, this is the proton spinning that way, versus both protons spinning the other way. There is another aim, which I will not talk today about, is the direct determination of the anti-quark polarization using production and parity violating decay, the W. If you know this collision at high enough energy, and we do that at 500 GeV, we start creating Ws. And now Ws, the pluses and the minus, we have a way to know that by looking at the decays. And they're produced from U d bar or du bar. So you can now play with the spin of the proton and see in which direction of the U d bar pair combination you see an asymmetry. And you can determine the spin combinations. I'll ignore it for now. I will come back to it if there's a question in the question hour. And then there is a systematic study of the transverse spin phenomena. This is the essential part because I'm going after the orbital motion. Now, all the time I've told you that the quark was spinning along the proton. The gluon, I'm trying to understand whether it was spinning along the proton or anti-direction. But orbital motion brings you in the third dimension. Remember, it is the radial rule and says this is the orbital motion, which means that the proton spinning that way, the quarks must be spinning that way. So I have to necessarily go in a transverse direction and look inside the proton. That means I'm for the first time acknowledging that the proton is not a linear, a flat object as we have thought about in the past, as a momentum in one dimension or a form factor in the other direction. Right? You have to mix those pictures now for the first time. And I'll show you something that we have seen in these collisions that definitely gives hints of something beyond the linear dimensions. But I will also tell you that with PP collisions, it's impossible to measure them quantitatively. You can see hints of them, but not quantitatively. And I'll show you the last part of my talk, how we will measure them. All right, so here was the new collider. It was built for heavy ion collisions, but we realized by adding a few selected magnets called the Siberian snake magnets and spin rotator magnets, which we built at RHIC and at RHIC in Japan, we could do very beautiful physics with these polarized protons. What was essential for that program was to maintain the polarization through the acceleration cycle of the proton. So the way it happens is here, the polarized H- source creates large number of H-. It gets through the LINAC at 300 MeV, then it goes through a splitter magnet, strips out the two extra electrons, and now you have positively charged protons into the booster at 2 GeV, then into the AGS at 24 GeV, comes out, and then bunch by bunch we put them into the blue and the yellow ring. These are the two just named blue and yellow for historic reasons. And then at two different places, the PHENIX and the star collision points, they collide. If the spin, the stable direction of the protons inside the ring is vertical. I told you that I want to first study the Gluon distribution, for which I need to do collisions that way or that way. That is done by the spin rotator magnets around PHENIX and star. Okay? You turn them on, and when the proton comes like this, goes through, and then the other magnet makes it vertical again, puts it back into the ring in the vertical direction as it was. So this is how this combination goes. There are polarimetry ideas which are vertical. We did not know how to make polarization measurement when this thing was coming up. We just trusted that we will come up with a method. We went ahead. It was a different time, just 10 years ago. We couldn't do that today. If we didn't know how to do it, probably we will not get funded. But that was something that people think was so essential that we would finally do it. And fortunately, we were able to do it. So I'll show you how we did that. So how do we know that the proton beam are polarized? And how do we know that they're longitudinally polarized or transversely polarized when they collide? How do we, as an experimentalist, absolutely make sure? Two different problems and two different solutions. So here is a proton which is spinning out of the, so this is the direction out of this board here, collides with the unpolarized proton. It was known that such single spin asymmetries, single spin, so you have an unpolarized proton, a polarized proton hits it transversely, and you create left-right asymmetries that are associated with the transverse motion. We understand it, but we knew they existed. So we decided to use this in a particular region, Coulomb-Nucleon interference region. We don't want very high energies. This is a region where Coulomb and strong forces can interfere. And we knew that there was a Schrodinger's calculation actually in 1946, what the asymmetry should be. And we had to measure that. We didn't know this polarization, but we knew the theoretical value, and we tried to do it, and we succeeded, as is shown in the next plot. This was Swinner's calculation from 1946, and we came up with this data point. In the Swinner's paper, there were some uncertainties which he said we don't know how to estimate even at that time, but we found that those uncertainties were extremely small for our value. So we knew that we had a method to understand the polarization. So as soon as we saw this curve, we knew how to measure the polarization. Basically, that M1 and M2 on the right term in the previous plot we measure. Schindler tells us what the single spin asymmetry is, and the only thing that is unknown is the polarization term. Go. Okay, I'm going to give up. All right. Now the question was, how do we know that it is longitudinally polarized? Again, the same idea that I showed you now, we have to come up with a trick. Now the transversely polarized proton hitting something unpolarized, and we create left-right asymmetry. Suppose the spin rotator is working. That means that the proton is now longitudinally polarized. Instead of this, it is coming that way. Now, all directions are equal. There shouldn't be any left-right asymmetry or up-down asymmetry. That means that you have a polarization, you see an asymmetry, you turn on your rotator magnet, and you should get rid of the asymmetry. And that's what we discovered. We saw exactly that. We did the experiment with the transversely polarized proton, with the unpolarized proton, and we plot as a function of phi the asymmetry of observed particles. And this was an accident. This is the first night that we tried this, we were looking for pi zeros or photons in asymmetry, because that's something we knew existed from previous accidental discoveries as well over the last 20, 30 years. And we were looking for such a thing in this, and our students told us, no, there is no asymmetry in this region there, but the neutrons that are produced in here are showing a huge asymmetry. 6% asymmetry was seen that night. And this is the first plot I showed. Now we have lots of precise plots. But this is what we saw the first night, that when the detector is off, that means the spin rotator is off, that means the plane is transversely polarized. You see this is the asymmetry as a function of phi in the blue beam. This is the same thing in yellow beam. As soon as we turn on the rotator, these asymmetries go away. And this was all the time going on, while at a different place in the rotator collider, we were continuously monitoring the spin of the proton with the other polarimeters that we had built. So we knew that the beam was polarized, and we were getting consistently, by turning off the rotator magnet, back and forth from here. So here is the result of all these measurements over the last 10 years. From 2003, at 100 GeV, these are the lines, dashed lines at 100 GeV. We started with 34% polarization, and 5 we had 47, and 8 we had some 48. So you can see as a function of time we were continuously improving the polarization. Not only that, this is the number of weeks in a particular run of a year. So you can see the slope, this is the luminosity accumulated, and you can see that as a function of time, we continuously were doing better in per unit time. In the last 3 months, we have now switched to the 250 GeV, which is the W physics program. I will be not talking about it unless it is asked in the question, but this is something that we are now about 50, 60, 55% polarization at 250 GeV. These are the only polarized proton beams at high energy in the world, and probably foreseeably in the future as well. I'll show you very quickly what the 2 detectors look like, and then I will go to results. Here is the PHENIX detector. There are 2 large collider detectors. This is the central part, the central magnet. On the left, on the east and the west side, there are electromagnetic spectrometers here. East and west, looks like a turkey. And it has particle identification, tracking, and calorimetry on this side, and similarly on that side. If you look at the beam's view, or if you look at the transverse view of this, then you will see in the forward region we have neon identifiers and the neon trackers. So in the forward region we have neon systems, backward region we have neon systems, and in the sides we have electromagnetic systems. I will not spend too much time on this beyond this point. I'll show you some results later. And here is the other large detector, the collider detector, solenoidal magnet, the star detector, and that looks more like a real collider detector with large acceptances. And they have the time projection chamber in the center, beam counters to detect the collisions, trigger barrel, a forward calorimeter in this region, and the end cap detector. So this really looks like a real detector. Ours is much smaller. We went for resolution and reduced acceptance. Star went for large acceptance and reduced resolution in terms of balancing the funding. All right, so let me go and show you some results and some arguments for delta G. So here is the measurement that I'm looking for. It is the double longitudinal asymmetry when the two polarized protons are colliding parallel versus anti-parallel divided by the sum. That is proportional to the Pion distributions in the first proton to the other side divided by the unpolarized times the analyzing power, because this is a spin asymmetry. The analyzing power of various partonic are well known, and what was produced for us by theorists was the curve as to what fraction of the, as a function of PT, what fraction of the total number of jets in this plot, for example, are produced from blue-blue scattering, quark-blue scattering, or quark-quark scattering. I'm sorry, this is a green curve which is not very clear. But as a function of the Q, this goes up, this sort of remains the flat, and the gluon comes down here. So if you did measurements in this region, you're looking at predominantly glue-blue and glue-quark. If you do experiments here, you're looking at predominantly quark-quark, quark-anti-quark, and quark-glue. So based on all this, you determine where you want to be. PHENIX determined the experimental measurements here. So Star went with the jets and went a little bit further in that direction. Again, there is some experimental emphasis that I want to make here. We filled up the benches, the proton benches I showed you. We had control of the spin. So the blue beam, for example, was filled with plus, plus, minus, minus, plus, plus, minus, minus. This is all under control. And the other one is plus, minus, plus, minus, plus, minus, plus, minus. Each bunch is separated by about 100 nanoseconds. So every 100 nanoseconds, there is a collision in the experimental area between plus, plus, the next one is plus, minus, the next one is minus, plus, and the fourth one is minus, minus. Remember that rotation that I was talking to you about? Because we wanted to make sure that all the numbers of protons had to be equal, and we had to have equal number of collisions in different combinations. This is solved very easily. We had to do that 8 hours and over months. This we do every 100 nanoseconds. And the second thing is that this bunch configuration, the collisions being at 100 nanoseconds, you don't expect the detector to change between collision to the collision. So your main problems of false asymmetries in all spin experiments, which came because you couldn't control the detector, all the beams, all the incoming beams to that level, is very beautifully solved in a collider just by the nature of the collider and the fact that we can control it. So this really became a very exciting thing, and we can measure this. In the first one itself, we got all the false asymmetries down to about 10 to the minus 4. Yes? About 100 nanoseconds.
That's enough for you to, if you can do the correlation between bunches.
Oh yes, absolutely. We can go all the way up to 25 nanoseconds if we wanted to. Just like LHC. The problem with LHC is that there are multiple collisions in bunch crossings. In the early part of our run, we had only one collision, 0.5 to 1 collision per bunch. Now we are getting into regions where 20% of our bunch crossing collisions have about 2 to 3 collisions. We've reached that luminosity at 500 GeV. So that's a big difference. But with the nuclear collisions, which I'm not talking about today, we already have 2,000 collisions in one bunch crossing. But we don't care at that point which bunch crossing it came from. Here, we want to keep track of those correlations, and that's why it's important. Anyway, so the first results came out 4 or 5 years later, and here is what we saw. For PHENIX, the Polarization asymmetries were measured, and look at that. This is 0 here. And these were directly proportional to the Gluon distribution functions. This is a jet asymmetry that comes out from star detector, 0. So what does that mean? It's shown here. This is a new global analysis of the same Gluon distribution I showed you before. The curve that I showed you, 1 plus minus 1.5, is right here. I can't even show you on this plot. It goes all the way up here. 1 goes here with a large uncertainty that covers everything. The new plot that was now produced shows here. This is the plot of the best fit that comes out of the new analysis. And the Gluon is the uncertainty that is quoted at 2 sigma. Okay? So the point I want to make is that the data are all between these 2 dead lines. As soon as you go to a region where there is no data, uncertainty should and do range go up again. And those uncertainties are something that we cannot handle anymore. We have to do something else to go there. And there is a method to go there as well, and we are planning to do that in the future. But in the region that RHIC can control and produce data, there is no contribution from the Gluon. This is the second crisis, if you want to call it. The green band is a chi-square difference of 1. The yellow band is the chi-square difference of 2%. These fits are done with 300 data points in 10 parameters. So delta chi-square of 1 is not accepted as the right way of interpreting the uncertainty. So they show what it is, but they show the 2% uncertainty as the more acceptable one. So we take the 2% as the one. CTEC has this recommendation, and so we do the same. Sorry, let me see. Sorry, what are you saying? Yes.
So the green band,
yes,
toward X, is becoming thinner, right?
It's X times, so it is plotted as X times delta G.
Yeah, so the X-axis is purely the X.
Yes?
Yeah. Now when we look at the yellow plot, when we go to smaller X,
Yes.
it becomes much fatter. The yellow
Well, I'll show you something else later. I'll show you some extrapolation here. It starts going down at some point. Just below this point, I'll show you something. It has to go down because it's always multiplied by an X. As long as the Gluon distribution doesn't go wider than 1 over X, this plot has to go down. And both do. Both do.
It's for 2 different delta chi-square. I was wondering why the profile itself is changing.
So the chi-square doesn't come only by changing the parameters of the delta G, it has other correlations as well. So it's the matrix of correlations is from quarks, and all cross correlations have to come in. So it's as I said, it's a 10 or 11 parameter fit with 300 data points. So you're right, and you expect it to go down, and it does go down, but it is not uniformly the same at every X. I'm sure I'll have a plot later, which will make that hopefully clearer.
It's also non-zero at certain X.
The what, sorry?
It's non-zero at certain X.
Yes, so if you look at, yeah, of course. So the question then, but there's an uncertainty there too. Yeah, there is uncertainty there too. This is the region where we have seen in the deep inelastic scattering, the Ormond experiments, fixed target experiments. All the lines are flat. Remember that. The slope there has to be 0. This data point, this curve is telling us that we are close there, but it has some freedom because it has to fix in the RHIC region where is the most profound and most powerful set of data that have come from STAR and PHENIX. They say, no matter what you try on the other side, this has to be 0. This is a direct measurement. So that tries to make the fit 0 in this region, and then there is a remaining part, which is constrained by the deep. And we'll know how to do that. Again, come back to it a little later. Let me switch to transverse spin. Okay, so let me point to this out. This is the best fit curve, finally. And it's a very small number, 0.02. And if you look at the chi-square, delta chi-square of about plus 9 or so, it goes to about 0.2. So that's the ballpark figure that people quote. Let me show you what happened with the spin. Again, that's a second Gluon crisis. It's a surprise again because we expected a large Gluon contribution. We see nothing. Now let's look at the transverse spin. Here is the proton coming transversely and hitting an unpolarized and creates a pion, in this case, just to pick something left and right. And you look at the left-right asymmetry, n left minus n right. And Kane, Pendleton, and Redco in 1978 wrote a very nice paper where they analyzed this and said, based on the knowledge that we have of the quark parton model at that time, this was much later, you expect that the total contribution from this of such an asymmetry should be proportional to the mass of the quark divided by the PT times alpha s. A very small number, it comes out with 0.1%. So people said, oh, the transverse spin asymmetry should be all zero. You shouldn't see anything. It's true, right? You have a large momentum pion or proton hitting something, and you're asking it to create something on the left-right scale because of the transverse momentum of the quarks inside. A 5 GeV, 10 GeV proton, and the quark has a transverse momentum of few MeV, hundreds of MeV. So you expect these things to be small, and this is what the equation was telling us. Okay, everything is good. Now people measured it. And what do you see? At center of mass energy of 5 GeV, you see a pi plus and a pi minus, very systematic, of how many percent? 40%. 400 times larger than what was predicted by the theory as we understood it now. You move it to a higher energy. People say, oh, that must be very small. These must be non-perturbative effects. So let's go to a perturbative regime. Let's see what happens when we really want the large energy of the pion. So this is the plots from 5 to 6.5 GeV to 20 GeV, and the final measurement is a 62 GeV. What stands out is that pi pluses and pi minuses show the same trend, and they show the same asymmetry. No dependence on the center of mass energy. Not only that, we did make this measurement at 200 GeV. And we saw a large asymmetry exactly as we saw it. And we saw it now. We did a very detailed analysis as a function of eta, where in the detector it goes. And we see that there is a large asymmetry no matter what. And if you can tell me, we'll be very happy why they come. So now we say, okay, well, what are the possible mechanisms of these asymmetries? These are huge asymmetries, 400 times larger. There are two mechanisms that are envisioned so far. Sievert's mechanism was due to Dennis Sievers at Michigan. The asymmetry is produced by of a final jet or whatever you're looking at is sensitivity of the transverse motion of the parton before collision. So you see this kT in the parton before collision in the polarized proton, and that gives rise through the final state. And that's very intuitive and very plausible, absolutely plausible. And that is really what we're looking for in the orbital motion case. So if I see such a thing, I will determine, I will deduce that, aha, there must be a kT, but kT in a finite proton just means that the momentum has to turn around somewhere, so it has to have an orbital motion component to it. But John Collins pointed out that there are other mechanisms of getting these things out in an asymmetric way. And he said that, oh, we have a polarized proton, then we create a quark which is polarized after the collision. It has a spin correlation from the original one, right there, and that might be the reason why that quark might have a kT. So this is the final state effect. And this is the kind of thing that you then can't resolve. So in any experiment, you will see these two effects all the time in PP collisions. And determining which part of which combination is how much is all dependent on the models that you choose. And that is the reason you can see these effects in PP collisions and are essential because in deep elastic scattering we would not have learned about as much as we did now here. So the way I look at it now is the proton-proton collision is the laboratory for QCD, whereas deep elastic scattering is the measurement place where you do the measurements. Then you test your ideas about QCD and perturbative QCD once you go to PP. So these are the two things which we want to now understand. We have made measurements. This is the pion at 200 GeV. This column is for 200 GeV. This column is for 64 GeV, 62 GeV at RHIC. The first one is pi plus, pi minus, pi plus, pi minus. We have k plus, k minus, and that's the amazing thing. The difference between pi and k is the strange quark, or SS bar, and suddenly you see a asymmetry which is all small but on the same side. The same thing happens at 62 GeV. At Browns, they make measurements of the proton as well, created probably proton, and you see PP bar production. Unfortunately, they did not make a measurement of the P bar in this run at 62 GeV. But this is the data we have. We don't know what the resolution of these things are, and we need to make those measurements in a different way because of the complication that I told you now. And that brings me to the last part of the talk.
Wasn't there something for lambda naught also?
So, I'm sorry?
Wasn't there something for lambda naught also?
asymmetries associated with lambda, but they are longitudinal spin asymmetries. Yeah, you're right, and they may have correlations to the strange. If you can start looking at these quark structures and start correlating all the asymmetries, one has to go in that direction. And it's the transfer of the polarization from initial to final. That was the crucial thing that people did not appreciate to start with. Anyway, we will make measurements now. This is an ongoing program to do the anti-quark, which I did not talk about, but I might comment later if there is a question. Transverse will be studied very systematically. I told you that the Gluon distribution is sort of at the impasse because we need to do something better. We need to go to the lower X side and really produce lower uncertainties, and that's not obvious from this method so far, and I'll tell you what that should be. So the Gluon distribution comes out to be about this. The uncertainty is large, and how do we go to low X? The orbital motion is obviously there because something is going on with the transverse spin, but we can't quantitatively measure that. And for that, we need to go and measure something called the generalized Proton distributions and deeply virtual quantum scattering. And we need a different kind of experiment, going back to the deep inelastic scattering, but with the knowledge that we don't want to be in the fixed target regime. We want to go to lower X, which means we have to go to higher energy. We have to have a collider like HERA with polarized protons. We have the polarized protons already at RHIC. We would like to add an electron beam to it. It's called the ERIC, which is the facility that is shown here on the left-hand side. There are two proposals being considered right now. One is the Brookhaven one, which is you have the yellow and blue beams, and we are proposing to add an electron ring, which is a blue, which is red here. It comes out, the source is right here. There are two LINACs, 2.5 GeV, 2.5 GeV sitting in these two regions. And so each pass, single pass of the electron through the entire ring boosts the electron by 5 GeV. And there are 6 vertical stack rings, 1, 2, 3, 4, and each of them is a fixed magnet. So 5 GeV, we use one ring, then it goes to the next one, to 10 GeV, it goes to the next one, and third one, and the fourth one, and the sixth one. We can go to 30 GeV, at least this is on the plan. The 30 GeV collisions with the existing RHIC beams in the existing experimental halls with PHENIX and star evolve into E-PHENIX and E-star at a future place. And we have an additional area where we could build a new detector. There are 6, this is part of the whole thing. It's 1.2, it's about 10 inches, this part here. And it fits entirely in the, I have a cross-sectional plot if you want to see. It's just a single thing. It's like this. These are 2 centimeters each. This part, each one is 2.5 centimeters from here to there. For each one ring. This is a permanent magnet. The cost, so to reduce the cost, we have a single magnet or single permanent magnet, and we just go from one to the other. We will use the same ring for that. That was how we were told the cost will come down. Collisions are right here. In the PHENIX and star, we call E-star and E-PHENIX, and we have an option of colliding at new experimental area. Sorry? Oh, I have 5 minutes more. No more. Remember I told you I need a very large Q-squared range because of the Gluon distribution measurement I wanted to make. And on the left-hand side here, I see what I can do. These are the existing XQ-squared measurements in EP scattering. And what I can do with the first phase, we're trying to do this in 2 phases. I got distracted. There is another proposal which is based in Jefferson Lab, which is presently going to upgrade to go from 6 GeV to 12 GeV. And then we can take the 12 GeV beam out here and then collide with a new facility which they are proposing to build, which will have essentially the same characteristics of the heavy ion collision here. So there are nucleons or polarized protons, but it's a bow-shaped design. It's a very novel design. And then you could have collisions in, again, 4 experimental areas here, here, and there. Some of them are used for something else. Then at the next stage, they would want to go to a higher energy. Then you would go to a larger ring. But this is a proposal that is technically being developed right now. the final value energy-wise and the characteristic of the beam-wise are the same. So here is the AP xq squared range for the first phase, or the final energy of 140 GeV in center of mass. And I told you that we wanted the q squared range, and here is what the q squared range that you get. A very wide range in x at very low x, 10 to the minus 4. It's not as high as HERA, but it is what it is. And you can do also the nuclear collisions. I didn't talk about that at all, about the nuclear initial state of the quark gluon plasma that you will hear about in other talks tomorrow probably, or today. You want to know what the initial phase, how did the quark gluon plasma come about when you collide nuclei, and that's something you can study as with the nuclei. The science goes, then the whole picture is a very wide one. The precision C and the gluon spin is only part of this whole picture. Oh, I'm sorry, I'm pressing the wrong buttons. The blue ones in the transverse momentum distributions and the generalized Proton distribution functions using the semi-inclusive gives in a wide x and q squared range, gives the full three-dimensional proton and position and momentum distribution now of partons inside the protons. And then, as I mentioned to you, the extreme high gluon densities that come as initial states of the nuclei, this is the QCD part, the non-QCD bread and butter of this future collider. But we also have explored recently, because we have extremely large luminosities, about 100 times that of the one that we achieved at HERA, 10 to the 34 in luminosity now per centimeter square per second instead of 10 to the 31 or 32. We are trying to see what kind of electroweak physics, precision electroweak physics, we can do with such a facility. Just to give you a glance of what can be achieved, this is a familiar plot to now. I've shown you this plot twice. If you did this experiment with the EIC, even in the first phase of it, you would get uncertainties that are expected of this range, this dashed red line, which will reduce the uncertainty from the present 0.4 to about 0.02 or 0.03 in the total integral. And to answer somebody's question there, you can start seeing, I was only showing up to this point right here in the X region. If you show it lower, you'll see that the X really comes out very fast and reduces this. So this really does start going down. There is no mystery or magic there. So a chi-square plot of how that would look like. This is the current delta G versus delta sigma plot. These are the uncertainties as we know of today. With the EIC data, you would start getting uncertainties, islands reducing like that. The anti-quark distribution functions and their spins also start getting reduced from the yellow bands to the red band. I did not talk about that today. I want to finish with these final few things about the generalized Proton distribution. I just barely mentioned it. I want to give you a hint about what it is that we are talking about. This plot of the Proton distribution function. It is a function on one variable, x, the Borkian x. This is the form factor measurement. This is also known. Proton distribution function tells you something about the fraction of what is the distribution of momentum of the quarks or the protons inside the proton. Whereas this one tells you what is the transverse distribution of these protons if the proton is coming at you, right? This the size of it. So that's what it is. And we always felt that these were, at least when we grew up, and probably you too, we felt that these were two independent things which have nothing to do with each other. Well, it's the same proton. They have to have something to do with each other. How are they connected? Look at it from a unified picture. There's something called the Wigner distribution, which is a function of x, kt of the transverse moment of the parton, and the radial distribution r of the parton from the center of the proton. If you integrated that over dr square, you get something like xkt, which is the transverse momentum distribution, which is what I was talking about to start with. I want to get the transverse momentum distribution of a parton inside the proton. So this is what that is. It tells you how are the partons moving transversely as the proton is coming at you. On the other side, there is a something called the generalized Proton distribution function. You integrate over kt and dz, and then you get these GPDs, generalized Proton distribution functions, in which what you are doing is you are not destroying the proton to look inside. You are looking at the internal structure with the electron. As I said, that photon that went in the way to measure that actually, deeply virtual Compton scattering, you don't want to destroy the proton when you want to look inside. You want to play with it a little bit. The reason why I want to do that is a simple example. If you have a glass bowl and you have water in it, and you have 3 ping-pong balls in it, and then you churn it, and it's moving now. This is your proton. You want to make measurement of the orbital angular momentum of these components, of these ping-pong balls and the water. You will not take a cricket bat and hit it like we did in the past to destroy the proton, right? Because by hitting it, you're destroying the proton, you're destroying the orbital angular momentum. How do you measure it? You will not measure it. What you want to do is softly go in with the paddle and see how fast the proton hits you, or the proton hits you, or what pressure you feel by pushing this paddle inside the water. There are the paddle, without breaking this whole proton. To do that, that kind of a reaction is called the deeply virtual Compton scattering, where the same kind of deeply electron-proton scattering, but the photon goes in, it doesn't destroy the proton, it plays, it tickles the quark, excites it, and the excitation of the quark will give rise to a real photon, and in the physics detector you measure the scattered electron, because there was interaction, the unbroken proton in the final state, and a real photon. That's called the deeply virtual Compton scattering. And if you did the same thing with a deeply virtual vector meson, final state, you were playing with the gluonic system in the water. So those are the 2 kinds of measurements that give rise to these GPDs, or they would tell you something about the GPDs. But my point is that you can get, by integrating various distributions like this, you get to the PDFs, you can get to dx integral and Fourier transform, you get to that. The only reason people thought about these two as disjoint, because there was not much we could do experimentally to correlate that. Now we have developed experimental tools to measure each of these things independently. And make the full picture from transverse form factors, transverse charge, and the structure functions to a 3-dimensional picture, which is a combination of the two. Anyway, if you did this with this electron-ion collider, you would start getting the pictures, brain MRI pictures, or any body MRI pictures that you look at, beautiful colors. But this is what it is. It's the KY, the transversely polar motion of a quark, U quark, versus the horizontal transverse motion, Kx versus Ky. You can start getting, so you can get flavor lines, what is the distribution of the momentum inside the proton. Similarly, using the GPDs, you can start getting position distributions, and the two together start giving you plots like this. You've seen this in the historical textbook in form of the structure of the nucleus itself, for example. What is the distribution? Now I'm showing you what the quark distribution is inside the proton or in the nucleus, for example. And this is the momentum distribution, this is the position distribution. With these, if you know the position distribution and the momentum distribution, you have, in fact, the total information you need to decipher the orbital angular momentum of a particular flavor at a particular momentum. So that's the way to go in the future. Before I end, just because Professor Manu asked me about the experiment yesterday, the same method that we are using, we can start making measurements of single polarized asymmetries. That's a parity violation experiment, which allows you to make measurement of sine squared theta w. What you need is a tremendously high luminosity, which is why this is very difficult to push the luminosity to its limit, and you want to keep the beam extremely stable over the experiment because these asymmetries are extremely small. These are atomic parity violation experiments. Sine squared theta w. Sine squared theta w, if you, I presume everyone knows because you probably have a very good high energy background, it is the rounding angle that relates the mass of the w to z, and et cetera, an extremely important parameter in high energy physics. But it runs as a function of the scale. These are the measurements that exist at SLAC from LEP and SLAC. These are the experimental measurements from parity violation in cesium and neutrino DIS and E158 experiment at SLAC. There are 3 proposals which are being made. The Moore experiment at Jefferson Lab, the QVeek is operating already, and the PVDIS. But we thought that with the electron-ion collider that we are just proposing, what you could do, and this is something that we can measure. And the theorists tell me that the slope is sort of important to tell us something about the curve. The running of the sine quarter W itself tells you about the standard model versus non-standard model effects.
Sorry, LHC is not added.
Actually, LHC doesn't, but what I showed you was LHEC. Yes. LHC will add to it in the same direction as the, I would imagine the forward backward asymmetries that teletrons are at some point. But they're at higher energies here. I don't know the significance of it in this context, but this plot comes from LHEC, the proposal to have an E with the polarized beam. Okay, I want to finish this talk now in last 2 slides. Spin is a useful tool. I hope I try to convince you that it's always a great tool to do physics, not just in particle and nuclear physics, but there are other things that we have done as well, which came out of our early experiments with fixed target experiments. Remember, we did experiments with protons, but we also did experiments with neutrons because we wanted to see what were the differences between them for good nuclear physics reasons. And it turns out that you can't have free neutrons, as you mostly know. So we use helium. And helium is a good surrogate for it because there are 2 protons, helium-3, 2 protons and 1 neutron, and the 2 protons anti-align EV to each other, and the remaining, which is the neutron, gives the property to the neutron is then surrogate, basically. Helium is the surrogate for neutron. But we also know, so we can do all the things that we did with polarized target with the proton as we did for the helium. But we also know that helium is inert. That means that you can actually inhale it, and your body doesn't react other than you talk funny for a while. That's the only thing that happens. So this, one of our colleagues said, what happens if we do an MRI with a helium? It turns out that it's an extremely important technique that came out of this experiment that we did together at CERN and at SLAC. It turns out that when you take a normal MRI, it's the proton that counts. You are kicking with an RF kick the protons, you excite them, you de-excite them, what comes out is measured in these detectors around you, and you get your three-dimensional picture of your brain or your body. And it only works if there's a proton, that means hydrogen. And you have lots of water in your body. And that's good, because you can see the inside of your body because of that. But what if we want to see what's wrong with your lungs? You hopefully don't have water in your lungs. If there is, then you will see it with that hydrogen MRI, and that's a problem. But if you have something else that is wrong, you don't have this tool. That's where this picture came in. We asked our students to inhale the helium. They all loved it because they can talk funny with professors. But at the same time, they started taking the MRIs. And amazingly enough, so I'm going to skip some of these. I already mentioned all this. I've told you what the technique was. And I'm going to show you just what happens. So here is the conventional MRI, protons, in the bloodstream. So this is what it looks like with the proton, right? You have blood flowing through the animal, and then there is an exchange of oxygen from the, so you're seeing that, those are the blood capillaries. But you don't see the structure of your lung. You don't see, you see the background of it, border of it. You see the body part, the hydrogen, whatever is there. But when you inhale helium, you start seeing the entire, this is actually part of a film. It's an online film. You can actually look at online, everything that you're inhaling and exhaling. This part here. You can see there's a dark hole here. That's the conventional MRI of your lung. And then you start seeing this helium MRI, and you can see all the lesions, all the problems that could occur. So this technique now is used very standardly to monitor if you have serious lung disease or a lung problem. This is something that is being used now in some of the hospitals to measure that.
This is not diseased lung.
This is not a diseased lung. I didn't want to show diseased lungs. But the amazing thing is, we experimented with our football teams. And football teams, these were very energetic, very fit people. And we started seeing lesions. We started having holes or something unusual. And we asked them, do you smoke? Because that was the obvious thing. They don't smoke. Is there any other history of lung disease? We found out that in their family, they had asthma or some genetic things. They had no symptoms of those, but we could detect them by looking at these plots or these pictures. So it's now being utilized. Now helium is a little expensive. It's very expensive to have helium, but the tool is very profound. People are going to Xenon to try to do this. But particularly proud when we published, when my colleague who actually did a lot more work in radiology, he published this. After 9/11, the police and the fire brigade that went in to help the people, they have very serious lung problems. And this method is now being used for every 6 month monitoring of their lungs. And it's been very, very useful to see how this develops or what medicines is doing and all that. Anyway, I thought that I would give a flavor of this. So completely unexpected things in spin also grow out of nuclear and particle physics to help us. Hyperpolarized is a good question. It's under pressure. It's because it's not you can't really polarize it as we did in our target. You have to have high pressure to maintain it, to transport it. This is the polarization of this is produced in Germany. Actually, there is a company that does it. They put it on magnetic bottles in high pressure and polarize it, and they send it to wherever you want to send it to. So that's what polarized helium, yes. But it doesn't stay polarized for too long. It doesn't stay polarized for too long. You have to cool it to cryogenic temperatures and put it under a lot of pressure. Then it remains. That's why it's hyperpolarized. Well, hyper pressure polarized, whatever it is. Anyway, I don't want to discourage you from looking at it. The timeline for this electron-ion collider, maybe I went one ahead. I did, yes. That's my summary. So spin, in my mind, is equivalent to surprise. It's a powerful tool in physics and very useful property that can be used outside of nuclear and particle physics as well. There have been 3 generations of polarized scattering experiments when we believe that we just scratched the idea of what this understanding of the nucleon spin is. But that's not the only aim we should think about. It's really telling us something fundamental about QCD, and that's really what we should be doing it. And the tools that we think we need is beyond RHIC. We need this electron-ion collider, which will do not only the spin in QCD, but also beyond. So thank you very much. Sorry, I went a little bit too far, but...
Let's have some few quick questions because we are really running short of time.
And there are questions in the middle too, so...
Yeah, this is a quick question. In the semi-inclusive reactions, you looked at pi naught, k,
yes,
and other things. What about direct photon and dimuon?
Yes.
Is it possible to...
Yes, the direct photon is part of our program for sure. I will show you direct photon mainly because the cross sections are so low that we haven't seen significant asymmetries there. But as we run for the next 2 to 3 years, I assure you that we will see asymmetries from direct photon as well. In fact, I have a student, I'm pushing very hard to look at those things. Gehrlach here has the same issue. The cross sections are extremely low. So we either have to lower the center of mass energy, then we actually lose some of the interesting high PT region. But if we keep it there, then we have to run quite a long time. But it is coming now.
E772 did really inform me a lot of...
Correct. So we will repeat those at high energy. At RHIC, if we reduce the energy, we also lose some luminosity. So we can't really go and do the same experiment as with 704. That center of mass energy is out. We will have to sit there for a long time. But we can measure at 50 GeV, 100 GeV, and 200 GeV center of mass. And there we need to run longer than what we have been able to do so far. But we will definitely do that. That's part of our future program.
You're going to keep running now at 200?
At the moment we are running at 500 GeV. 500 GeV program will probably end in 2013. Then we'll go back to 200 GeV. And then, because it is a useful thing to do this for heavy ion comparison as well. So that is a big advantage. So we want to finish the 500 GeV now. Now that we are ready with all the detectors that needed for the W physics, we will finish that in the next 2 years. But we will do that time, we will also do Gehrlach. And Rohini left, but Rohini mentioned charm, anti-charm. So we put a detector, the silicon detector we just built at Stony, and it's now in the beam, and we will take charm, bottom separation, psi in the very forward region. All of that is coming now.
So this color octet stuff.
Color octet stuff and everything will come, yes. Students. Oh yeah, you're a postdoc. You have to, okay. Yes.
It turns out the contribution from the quarks part is small in the spin 1F, but somehow anyway we have a quantization of a spin or angular momentum, but why we only have 1/2 and otherwise like 3/2 or other quantum number, why we get only 1/2 spin in proton?
Why the proton spin is half? Somebody made a comment yesterday, I don't understand why. You made that, right? We don't ask why, we say how.
All possible like spectrum, if it is a mixture of 3 quarks and gluon.
Yes, and everything comes out to be half.
Yeah.
Why? I don't know. I would like to know. It's a good question, but I don't know the answer to that. I just want to know, I know proton spin is half. No matter what energy you scan it at, right? That spin is rather unique. Everything else changes. You know, I was telling some of the students the other day, there are 2 basic properties, the mass and the spin. As you go to higher and higher energy, mass becomes irrelevant because you're putting so much energy into this. Mass becomes irrelevant. But the spin is still the same. At Tevatron, we use the spin half, right?
How exact state of proton also gives us half spin?
Now, there are excited states of 3 quark systems. That is true. But they are not called protons. Those are other resonances.
So that also gives 1/2 spin.
Well, are you asking whether the play that we will have for quarks inside, or quark gluons inside the protons, should it be symmetric in other resonances? Is that what the question is?
Or for other resonance cases?
Well, it will be interesting to know. There are methods that have been proposed, but experimentally very difficult to measure those.
So theoretically, we even don't understand.
We don't understand that, no.
I have 2 remarks. The first one is a historical one. During the period from 88 to 95, there's a hard debate whether or not Arnald's Gluon contribution contributes to the first moment of the G1.
The Gluon distribution, yes.
For example, Atari leader
Yes.
and many other people argue that
I agree.
there's a huge Arnald's Gluon contribution
Yes.
to the first moment of G1P.
Yeah.
And they argue that if delta G is about all the 2,
Correct.
photon spin prices
2 to 4, exactly.
But Barbara Jeffrey and Manohar and other people say no. In the field theory, like operator product expansion, actually
Yes.
there's no analogous Gluon contribution to G1P, to
Correct.
the first model G1P. So there's a hard debate whether or not the operator product model is correct or operator product expansion is correct.
Correct.
But then later on, people realize actually both are correct. It depends on the definition of the data field.
I completely agree. Axial anomaly, how it separates delta sigma from delta G. That's correct.
My second remark has something to do with the delta G. The fact that the delta G is measured to be small by RHIC actually is not bad news, because in QCD, just a relation between the C polarization, delta strength C polarization, delta S and the delta G.
Yes.
Because delta S can be produced from the hard polarized gluon.
Correct.
Through the actual anomaly.
Correct.
Because anomaly will break the color symmetry. So through the color symmetry breaking, you can
Yes.
generate the delta S from the delta G.
Right.
But the delta S has been measured independently, like a Hermes, like a compass. And the delta S is very small, like a 0.02. It's actually consistent with 0. So if the measurement of the compass is correct, then delta S has to be small, and the delta G has to be small either.
I completely agree. Modular one thing. The reason why I did not continue working in Compass and went to a collider was everything that we want to extract from deep inelastic scattering had to use perturbative QCD. And perturbative QCD with the tracks of pions and kaons at 1 GeV was very dangerous in my mind. I did not like that. So your statement is correct if you assume and you accept that perturbative QCD interpretation is correct even at 1.2, 1.5 GeV. That is the biggest limitation. I know that there are arguments to go around it, but I wanted to go and do an experiment in a region where nobody will ask a question about my method and my interpretation.
But the PQC duration I just mentioned is quite robust.
As I said, there are arguments why they might be correct. Open charm, I would believe. I think there are answers of an open charm. That I believe. All the other things about semi-inclusive, there might be soft physics effects for asymmetries that will destroy my result. And that might be my concern.
My point is the fact that the data is small, C probability is small, the fact that the data T is small, actually quite consistent.
I agree. I would just want to make one more point then, that I want to make that statement in 5 years from now, or 10 years from now, when I actually measure the low X. Then we would all agree.
I think it's getting late. Could we end this session? Thank the speaker for a very
Okay.
A couple of announcements from the organizers. Please listen to it before you leave and come back. Hopefully by first, but let's see what happens.
Well, this is about the trip, so just want to tell you that if people who have not signed up, if a few more want to join, we still have some room. So please talk to one of them if you want to do that. Right now in the speedway, if you can. And also there will be dinner at MGM Resort on the way back from Mahabalipuram at 7 o'clock. So if people don't want to come to Mahabalipuram but would like to come to MGM, you can come, but you're on your own. So you'll have to figure out how to get there.